Let's return to Black Mountain, to Gallen Barrier. This should be, or hopefully is, familiar in some respects because it comes from Pukenmore. It's the paper that we opened up at the start of the semester, and in it Pukenmore highlight this obvious difference between north and south insofar as the composition of the overstory. And you can see on the left, on the north aspect, we have Eucalyptus rossii relative to Eucalyptus macrorinca, and you can see the relative density. That's in terms of percent of total stems on the individual aspects. You can see exactly kind of what we saw. And we went out there expecting, because we're familiar with Pukenmore, this great dominance of Eucalyptus rossii on north aspects. And you can see it's up around maybe 75–80%, macrorinca down around 20%. And then as we switch to the south aspects, the direction of that relation sort of switches, but it's not quite as dramatic as it is on the north aspect. You can see there's a dominance of macrorinca, but it's not at that same level. It's sort of more in the 2/3, maybe 70% range for Eucalyptus macrorinca. Now, if we switch to the quiz and we ask a question around stocking, then we could conduct this test between north and south aspects, or on north and south aspects. So I've structured things a little bit differently here, where you are comparing between aspects for individual species. Here I compare between species on the same aspect. And I compare, this stocking between rossii and macrorinca on the north aspect, and yes, assuming unequal variances, you can see there's a positive T calculated, so rossii must be greater than Eucalyptus macrorinca, and you can see that's highly significant if we're thinking about a difference. But here in this test, we wouldn't ask whether there's a difference. We'd ask a one-tailed test because we have prior information that indicates the difference is in one direction. So we can use previous pieces of work, pieces of research to indicate what direction we're expecting the effect to be in. We go to the south aspect. This one turns out to be an equal variance-based test. And you can see that the T is negative here, indicating that, of course, macrorinca is greater than rossii in that calculation. And we have a one-tailed test down the bottom there, that less than test, indicating that rossii, the stocking, is less than Eucalyptus macrorinca. So our data are consistent with Pukenmore's interpretation and their hypothesis tests. Now, one thing that's quite striking in both their data, in their paper, and our data, is that the difference on the north aspect is far greater than it is on the south aspect. And we can see that represented if we dig a little bit deeper, if we move past just looking at means. Means are useful, but they just give us, as the name implies, just the average condition. And there's a lot more to a stand, there's a lot more to a population than just the average condition. And you can see that represented here. You can see on the north aspect, you can see that the distribution of size classes is very different between rossii and macrorinca. Now, I'm not concerned here about the absolute difference in terms of numbers. What I'm interested in here is this very clear and very disproportionate relative frequency of stems in the smallest diameter classes in Eucalyptus rossii. You can just see that abundance, or that frequency just climbs. So there are many, many small stems on north aspects that are Eucalyptus rossii, and yet for Eucalyptus macrorinca that's not the case. Whereas on the south aspects, there's similarity, a little more similarity in their distributions. Now that difference in those distributions is what is behind this very large difference in relative density of rossii and macrorinca on different aspects. A difference in the underlying distribution generates a very different effect size depending on what metric we're looking at. You don't see the same scale of effect when we look at basal area, because of course basal area takes into account not just the number of stems but how big they are as well. And all of these small stems have a relatively small impact on basal area relative to larger stems. So distributions offer us something more, and to come back to the start of the course, thinking about distributions, distributions offer us more than just the means do. And here are our data represented in a similar fashion to Pook and Moore's. I've changed the histogram so it's a line rather than bars that you would normally see in a histogram. So our relative frequency here, you can see, like Pook and Moore, we have about 80% to 20%. The numbers are so similar, it's almost frightening. On the other side, though, on the south aspects, you can see things are closer. So consistent with Pook and Moore, and consistent with Pook and Moore, look at that difference in the distribution of stems within size classes. So there is definitely an underlying difference that is a product not just of changes in species composition, but also in terms of the way the individual species make up the stand, how they generate stand structure. And that stand structural difference, that's an important thing for us to understand from an ecological point of view, be it forests or any other population. So understanding distributions is worthwhile. And if we're going to understand distributions, we need to, like we looked at the start of the semester, we need to move away from looking at absolute values in terms of exactly how many stems there were. We need to look at relative frequencies, because relative frequencies remove things like, differences in sampling effort and perhaps differences in overall stand density because of differences in productivity. If we really want to understand structure, then we have to remove those underlying differences, things that affect the mean. So we can achieve some very nice population level comparisons once we start looking at the frequency of outcomes and compare between levels, as we can do with our Black Mountain Gallimbarry data. And we can do that with all sorts of data that generate counts, or surveys that generate count data. We can apply that kind of approach to count data that are yes, no's, or multiple classes like we have within dominance classes. So we could apply an analysis based upon distributions just as equally as we could to these little bar graphs here as we can to the big line graphs that make up the main page. And we can apply it, ideally, to survey-based data as well. So remember, online there's some content focused on surveys and ethics associated with surveys. If we conduct a survey, then we need a method to undertake some sort of analysis of similarity or difference between different levels or strata within our sample. Here, the one behind me, if you've had a look at that lecture, you'll know this sample data and you'll know the problem that was associated with this sample data, and that was that the authors calculated a mean for their data. And honestly, I don't know how you calculate a mean for the words very supportive, supportive, neither supportive nor unsupportive. I don't know how you calculate a mean for those things. Well, they just applied an ordinal ranking and then calculated the mean based upon that. And that's completely inappropriate, because the distance between being neither supportive nor unsupportive and being supportive is not necessarily the same distance in terms of, thinking and opinion and strength of emotion, or, how strong the logic associated with your argument is. That distance is not the same between each of these categories. So we can't say that there's a quantitatively similar difference between not being supportive or unsupportive, or being supportive or being very supportive. And not only is it non-constant, it's not constant between people. So we cannot calculate means and make comparisons of that nature for data like this. And if you've seen the lecture, you'll know that the ANU has conducted those very comparisons when we get our student evaluations of learning and teaching back. It's not appropriate, and that's one of the criticisms that universities consistently receive from their academic teaching staff, especially people who teach quantitative methods, around the application of student evaluations anyway. But what we can do is compare these relative frequencies. We can ask a question about, you know, are those two distributions the same? Has there been a change from 2011 to 2015 in terms of opinions around, say, for example, culling of kangaroos for conservation? We can compare that at a distribution level. That is arguably better than just an overall mean that doesn't really inform very much, is based upon numbers that are completely irrelevant. So we can, but how do we do that? All right, so let's take a moment and think about the concepts that we need to take on board. The first thing, if we take away our different levels within a data set, so our two different species or 2 different years in which we've surveyed people's opinions about kangaroos, because we can apply it just as equally to categorical data that summarises some continuous variable like diameter, as we can apply it to categorical outcomes or outcomes to categorical questions in a survey. So let's take out those 2 levels for a moment, and let's just think about one survey, here a survey of trees, that has produced a frequency distribution across one metric here, diameter breast height. Now this could be a question as well, your opinion of culling, your opinion of a course. Any other survey, you might imagine here on the x-axis a set of questions, Likert scale data, ranking from 1 through to 5, again in that survey design lecture, can produce a distribution like this. Now, when we think about comparing distributions from surveys, what we need to bear in mind is that data distributions represent a non-random outcome that's derived from our sample. So a non-random distribution, there's some distinct structure here that potentially indicates something about the people we surveyed or the underlying population. Now, as it stands, this distribution here is completely consistent with a population distribution that is applied very, very widely to understand population structures, referred to as a gamma distribution. We'll come to that a bit later. Oh. Now, sorry, the slides are going to be a bit funny today. All right, so if we assume that there is a random possibility here, that distributions can be truly random, that if there is no effect in a stand of trees that produces a diameter distribution, if everything is equal, then there is a random outcome in which all frequency classes are exactly the same. And we can come up with an assumed diameter distribution or assumed distribution for our survey responses. And we refer to our assumed or our expected, assuming a random distribution, expected and our observed as pi here. And that's the way that we reflect on our distributions. But in this case, the proportionate frequency or the proportional frequency of outcomes within each of these classes. So what's assuming null is true, that the distribution is completely random, we have a pi that is associated with each of these classes. Now, a couple of things to bear in mind is when we come up with an expected value, assuming a random distribution, we define that, sorry about it sitting down the bottom there, when I put this slide together it was sitting up higher. We need to define the number of categories that we're going to split all of our possible responses across. So across our 100% of responses, we're going to split our proportions equally between 1, 2, 3, 4, 5, 6, 7, 8, 9 DBH classes here. And so that gives us K categories, K number of categories that we can split our possible responses across. And if there is a completely random distribution, there's no reason for there to be any kind of pattern in diameter distributions, then what we would expect is that the proportion of responses in a survey, the proportion of trees in this data set that will fall within each category, within each diameter class category, will be exactly the same. So we just divide 1 by the number of categories we have. And that gives us the proportion we are expecting across all categories. And so our distribution, we assume, the distribution we assume looks like this rather than what we actually did observe. So we have our observation and our expectation. So we're back in observation expectation land again. So we have our expectations that if we have K equal 9 in terms of diameter classes, then we have an expected value of 1 on 9 or 0.11. So 11% of all of our diameter measurements should fall in each of these classes. And then it's really just a matter of comparing our expectations to our observations. And in this respect, and that's why we look at this now rather than at the start of the course, in this respect, the ANOVA and this approach where we look at the distribution of the frequencies within distributions, the ANOVA and this approach, the chi-square, are very, very similar because they take a very similar approach in terms of deriving the estimates of the final statistic. All right, so how do we calculate it and what do we assume and what's our H naught? So as you can imagine, if our expected here in the blue, that's our random distribution that occurs in the absence of any effect that determines the diameter outcome or a person's response to a survey. If our blue here is no effect and our green is our observed effect, then let's look at blue as our H naught. Our H naught in which the proportion of responses in our first category is the same as our second category, the same as our third category, so it's the same in 10, 20, 30, 40, through to the last of our K number of classes. That assumes that there is an equal chance of a tree falling into any of these categories, that there's no effect, no process that affects diameter. Or in a survey, there is no reason to assume that people have a preference one way or another or an opinion on something one way or another. So our H naught is that these two are equal. Now, you do not need to squint to see that these two are not equal. And this is, and I'll return to this, this is really the problem of this kind of base level chi-square test. That the difference between these two is absolutely obvious, begging the question of whether a test like this is necessary, but it's a good start. Now, how do we calculate it? Well, it's referred to as the goodness of fit or the chi-square test. So how do these distributions fit each other? How does our observed distribution fit the expected distribution? Now that we have identified an expected distribution means that couldn't we change our distribution to be anything we wanted, our expected one? Well, yes. If we had prior information, then we could switch things up a little. We could say, well, we have this prior knowledge around what a diameter distribution should look like in a forest type that's, say, been undisturbed. So let's look at the impact of a particular disturbance on diameter distributions in in a disturbed location. Let's compare the two. Sorry, I just had my mind just stopped there because I just had this moment where I thought, this is exactly what we should be doing with some snowgum data and dieback. Anyway, see you in the middle of a lecture and I say, we need it. Anyway. Okay, so how do we calculate it? And we'll come back. We calculate it because we have this chi-squared statistic where we calculate the difference between our observed and expected outcome within each category, square it. So this is a sum of squares approach again, and divide it by the number of expected. So we have a proportionate expression of the difference between our observations and expectations. We do that for every category, and then we just add all of those category chi-squares together to deliver a single chi-square statistic. And that allows comparison to be made. So we might go about it this way, where we make our observations in our diameter data. There are our observations. Based upon k number of categories, we arrive at a constant proportion that we are expecting within each diameter class. And you can see down the bottom here we have 1,977 observations. And if we sum all of those down the bottom, yes, we still have 1,977 in our expected column. And if we calculate our chi-square statistic, difference between observed and expected squared divided by expected, here our 219.7, then we end up with our chi-square. Now it's a simple calculation process that then gives us this value down the bottom. Now the similarity, and having mentioned that this is similar to the ANOVA, you can probably anticipate what's going to come next. Okay, well we've calculated a chi value, there must be a critical chi value, and we just compare chi calculated to chi critical. That's exactly what we do. The process is the same every single time. Once you get into the idea of critical values and calculated values, it is the same every single time. We're now comparing our expected chi, bearing in mind that there's intrinsic population error that contributes to sampling error, and it produces a range of possible chi-square values that might arise by just random chance. We need to take that into account just as we would for the F or the T, and then we compare that to our chi calculated. Now, how do we do that? Well, there's a chi table, and in Excel there's a chi-inv function, so we can calculate it just as much, or look it up just as much as we can anything else. What does the chi distribution look like? Well, it looks very, very much like the F distribution. Why? Well, because chi starts at 0. If there is no difference between our observed distribution and the expected distribution, then we'll arrive at an outcome of 0. Large values are increasingly unlikely, large chi-square values, and so we have a probability distribution very, very much like an F distribution. And like an F distribution, the number of degrees of freedom here, the number of categories, changes the shape of the distribution. A small number of categories leaves us with a large number of possibilities down in the smallest values of chi-square, and as k increases, this distribution shifts along the x-axis and is drawn out. So low values here are likely just by chance, large ones unlikely, and so that gives us the same method for testing whether a difference between two distributions is the product of a genuine effect or random luck. And you can see if something falls out here, we're inside the rejection region. And the same threshold, 0.05, 1 in 20 chance. So what happens if we change our distribution, the number of categories? Well, you can see, as I mentioned there, the distribution is drawn out. It's drawn out because with a single degree of freedom, that's two categories, there are few instances in which we can detect differences. With more categories, those possible differences, instances in which a difference might arise, they increase, generating larger chi-square values by chance alone. Interpreting the chi-square runs exactly the same way as we've seen so far, applying a p-value. Now we will look at an example of this in the second lecture today. Now there are assumptions and conditions that we have to bear in mind. The same condition that we've seen so far. Again, coming back to what we talked about at the start of the lecture around n and the nature of n, how n is obtained, the assumption here is that our observations are randomly drawn. But there are also some assumptions around how many expected outcomes we expect to see in each of these categories. Not observed, but of expected. Now you can derive different counts within expected values for different categories, because sometimes the instances in which categories become possible, and we will see that in a moment, that varies between different levels we might test. But these assumptions are met, then we can run a chi-square test. But if they're not met, we can still run chi-square tests. We just need to combine the individual classes or categories in a logical way. So we might, if we don't have enough expected values here in our 90 centimetre class, we can combine 80 and 90 and call it greater than 80. We can do that, but it must be logical, and they must make, in terms of logical, in biology and ecology, it must make ecological or biological sense. It can't just be some random pairing. Now, we did say a moment ago, a little while ago, that comparing these null conditions where we have a completely random distribution is, well, I suppose you can see it as a straw man sort of hypothesis. This is pretty easy to knock over. It's very unusual for distributions to be completely random. Rather, in ecology and in biology, there are a set of very well-defined distributions that have been consistently recognised and described time and time again, and are useful when it comes to testing chi-squared distributions or observed distributions against. And you can see a family of those distributions presented here, and you can see the kind of applications that we might apply those different distributions to. You can see this distribution down the bottom, a log normal distribution, where we have a right skew, a distinct right skew, just like our diameter class data is appropriate for using, for applying to size, for example. So rather than assuming a random distribution, we could apply a log normal distribution that describes perhaps density dependent or growth related processes and test relative to that. It provides some biological and ecological underpinning to our tests and tests whether our observations differ from expectations associated with the organisms, the ecosystems, whatever it is that we're working with, because those expectations are there. The assumption that things are just randomly distributed, it's just too flimsy to apply in any real context. What about when we have two levels then? This is definitely a case in which, well, it doesn't make a lot of sense for us to compare this distribution of Eucalyptus rossii to Eucalyptus macrorinca in this form, because neither of them has a completely random distribution. They are both strongly skewed, very much right skewed. Couldn't we compare those distributions to something other than just this null distribution in which everything has an equal likelihood? Well, that's exactly what we will do and can do, but bearing in mind it's 5 minutes to 1, we'll do that at 3 p.m. In addition to that, the lecture at 3 p.m. should give us time to analyse one of my favourite data sets. Well, I'll talk about that